Okay. Okay.
Okay.
And yeah. And now that we and another way that we can okay here, okay, and we have this, we say that okay, we can consider more spatial embedding, which what we call the elementary out embedding. We say that H is elementary if it can preserve not just quantifier free formulas, it can preserve any formulas between these two structures. So basically it said like up to like, yeah, logically these two structures, they up to your language L, these two structures are very similar. It satisfies the same properties. Okay. And another interesting thing is we can also have what we call elementary substructure, which and if we go into the other direction, we're gonna say that it is an elementary extension. Okay, so this is interesting because we say that M is a structure. M is an elementary substructure of N. If M is a substructure of N, and for every L formulas, phi x1 up to xn, and for any objects that is in the smaller guy, M, if M satisfies phi a1 up to an, then n must satisfy phi a1 up to an, and vice versa. Okay, so this is interesting. And here you can see that if M is an elementary substructure of N, then you can show that the inclusion map from M to N is an elementary L embedding. So here you can see some connection between elementary substructures and L elementary embedding. Actually, you also have the connection in the reverse direction. If you have M, you have a map H that is an elementary L embedding from M to N. There is a result that it's not hard to prove. You can show that there is an L structure N prime such that this guy is an elementary extension of M. So you can consider this as an inclusion map from M to N prime. And these two structures are isomorphic. My isomorphism symbol looks a little strange. Okay, here. And you're gonna have that this is there is an isomorphism between M and N and N prime, and N prime is an elementary extension of M. Okay, and you also have that this diagram is commute, which means that you can compose this and then this. You're gonna get H if you go this way and you compose with the inverse of this guy. You're gonna get the inclusion map from M to N prime. Okay, so which mean that from now on, when we have L isomorph L elementary embedding, we can regard that this structure N is an elementary extension of M. Okay, so that's some connection, and sometimes it's kind of helpful to help us like simplify our proof, right? To simplify our our proof, make it simpler because we can reduce from any elementary embedding to just substructures. Okay, and there is a nice tools that is what we call the Tasky word test that can be used to in order to show that two structures M and N. M is an elementary substructure of N. What you need to do here is you just need to show that for every formula L, phi x, phi xy, if A is in M to the N, which mean that it is in the smaller guy. If N satisfy there exists Y phi AY, then you can find a B in M such that N satisfy phi AB. Okay, so that's what Tasky word test say. Here you let me point out something. You can see that when we talk about the elementary extension, what we do is we're going to go from M satisfy phi A1 up to AN, right? If and only if N satisfy phi A1 up to AN. But in the condition on the right here, you can see that we can only reduce to consider only in N, right? Like satisfiability gonna be considered in N, but the object that we're going to consider here gonna come from M. Okay, so that's why it's reduced our work from consider every possible formulas to just formulas that is of this form. Okay, and it can be proved by using induction on the complexity of formulas. The forward direction is trivial. We need the induction for the backward direction. Okay, so that's what we have here. Okay, and here is another interesting result about the extension. That is what we call the Lowenheim-Golem theorem. So before we go any further, so let me introduce you a little bit more notation. Let M be an L structure and A be a subset of M. The diagram of M is the set of LA formulas, LA sentences, such that it's of this form. The diagram of MA is the set of phi and then CA1 up to CAN. So we add a constant symbol for each object A in here, and we denote it by CAI. Okay, and we only consider quantifier phi L formulas, and M satisfy phi A1 up to CAN. Okay, so this is what we have. Actually, this guy is related to the first example that we talk about in graph theory, right? If that here, if we have here VEW, let me recall you. This one, right? So here and here, not VEW. Actually, what you have in here, this is also contained in the diagram of your graph, when A is the set of all vertices. right? So we add every object in your vertices as your name, and then consider it here. And here you can see that every statement that we add here, they are quantifier-free L formulas. Okay, so that's what we call the diagram of M. And we also have extension of the diagram of M when we consider every possible formulas instead of just quantifier-free formulas. The theory of M in LA is the set of LA sentences such that it is of this form, phi CA1 up to phi CN, where phi x1 up to xn is an L formula, and M satisfy phi A1 up to AN. So we're going to collect all formulas that satisfy, that M satisfy, right? And use parameter from set A. Okay, and here we can have that, let M be an L structures and N be an LM structures. Then if N satisfy the diagram of M in the constant M, then there is an L embedding from M to N. Or in this case, you can imagine like M can be embedded in N, or M is in substructures of it. This is not precisely, but you can think of it that way because there is an isomorphism between these guys. Okay, and that's what we discussed earlier. If we want to be more precise on the proof of the graph theory one, what we need to do is this M gonna be your model of your G, but this guy N right here, it's gonna be an extension of your graph, right? And if you have a coloring on here, you can have a coloring on here as well. Okay. And similarly, you can also show that if N is a model of the theory of M in M, then there is an elementary L embedding from M to N. Okay. So that's, I think that clarified my a little bit vague argument above. Okay. And when we talk about Lobenheim's Golem theorem, there is several results that is very useful in model theory and also in set theory as well. Okay, here is the Lobenheim's Golem theorem. Lobenheim's Golem theorem say that if you have a set T be an L theory, and suppose that T has an infinite model, and if kappa is a cardinality that is larger than the cardinality of L plus Aleph naught, where this guy gonna be equal to max, right? Max of L Aleph naught, right? So if it is infinite, roughly speaking, if L is infinite, it's going to be equal to the cardinality of L. But if L is finite, it's going to be infinite. So that's what this one says. It's going to be, yeah, countable, at least countable, at least countably infinite. Okay. And if you have this, then you can construct a model of T of psi exactly kappa. Okay, so that's what we have here. Okay, so that's the Lobenheim's Golem theorem. If T has a model, infinite model, and then kappa is a cardinal that is larger than the language of L plus Aleph naught, then T must has a a model of size at exactly kappa. Okay, and the idea of how we can construct this is we can show that by using compactness completeness or compactness theorem. You can use either one. You can show that T has a model, the sketch, proof, sketch. So the idea of the proof of this one is if we can show that T has an infinite model, right? So first, we're going to show that T So what we're going to do is we're going to extend your T to T prime by adding sentences that guarantee that every model of T prime must have every model of T prime has at least is of size at least kappa. Okay, so the idea is we're going to construct a model of T prime which say that every model of T prime is of size at least kappa. And how do we do that? What we're going to do is we're going to expand our language L to L prime by adding distinct constant symbol, let's say C alpha, for every alpha less than kappa. Okay, and we're going to say that each symbols here are distinct. So here we're going to add the sentence, this sentence, T prime gonna be equal to T union with C alpha is not equal to C beta for alpha that is not equal to beta. Okay. So by doing this, if T prime has a model, it must have at least this it must have all the distinct interpretation of each distinct constant symbols here, which means that it can guarantee that it has size at least kappa. Okay, and by completeness theorem, you can consider a strong form of completeness theorem, which say that if T prime is consistent, then you can have a model of size at most. If T prime is consistent, right, then you're gonna have that T prime has a model of size at most L plus a left node, L prime plus a left node. And here you let kappa be, you know that the size of L prime is at least kappa, so this become kappa. So by completeness theorem, you're gonna get that if T prime is consistent, T prime must have a model of size at most kappa, but every model of T prime is of size at least kappa, which means that you're gonna get a model of size kappa. So right now, what you need to do is you need to show that T prime is consistent. And how do we show that? We're going to use this assumption that T has an infinite model and the fact that you can use completeness theorem. Okay, so which means that in order to consider this, what you need to do is you just need to show that for every finite subset delta of T prime, delta has a model. Right? But when you consider these delta, you can see that delta is a subset of T union C alpha I, C alpha J. For some alpha I, you have alpha. So you have alpha I be in some set of cardinal that is less than kappa, less than some fixed ordinal. No, that's not right. For when alpha and beta, nope. Alpha and beta, and you just pick only finitely many of them, alpha and beta in alpha 1 up to alpha n. Right? So you pick finitely many of them, you say that, oh, finitely many of them, they are distinct, right? And you can show that these delta has a model by, you can pick, you know that T has a model, right? Has an infinite model. So let's say that is the structure M, called M. And then since you know that M is an infinite model, what you can do is you can pick distinct A1 up to AN and distinct object in M. And we're gonna let C1 interpretation of C1 in here to be this guy. We can define interpretation of C1, Cn in our new structure to be this guy. And this is gonna show you that this new structure that we construct is a model of delta. Okay, so that's the idea of how we can show this Lowenheim's Golem theorem. Okay. And after we have Lowenheim's Golem theorem, we can also have two more versions of this, which say that for upward Lowenheim's Golem theorem, it say that if you have an M be an L structure such that M is infinite, and for each kappa that is greater than or equal to cardinality of L plus cardinality of M, you can find an L structures N that is an elementary extension of M that has the cardinality of that is of size precisely kappa, which means that if you start with a structure M, and you can consider the case that when L is countable, then you can find a structure N that is an elementary of extension of M that is as large as you want, right? You can, let's say you are given a cardinality kappa, you can that is larger than the cardinality of M. You can always find an elementary of extension of M of that size. So that's what we call the upward Lowenheim's Golem theorem, because we look up, right? Look at the larger structures. We also have downward Lowenheim's Golem theorem, which say that if you have N be an infinite L structure and you have S be a subset of N, then you're going to get that if N has an elementary, then you can find an elementary substructures M such that S is contained in M, and we can control the size of M. That M is of the size less than or equal to cardinality of S plus the cardinality of your language plus the Aleph norm. So that's what we have here. So there are two types of, there are three types of Lowenheim's Golem theorem. So the first one, it's implies the second one. And for the third one, you need a little bit more construction in order to get that. But I'm not going to go into the detail here. But this is very useful. So the idea is we're trying to generate this M by using to be as minimal as possible. Right? So we can consider these as your generator and trying to add more objects. And we're trying to make sure that we don't add too much. Okay, so that's the idea of the Dalbert-Lowenheim's Golem theorem. And actually, the Dalbert-Lowenheim's Golem theorem is related to the Golem paradox, which it's related to set theory. So, okay, it's related to Golem paradox. So let me just put it that way. Paradox. Okay. Okay, I still have several more to go. Okay, and next we can see that when we have a kappa, cardinality kappa, right? If kappa is large enough, you can find, if you have a structure M, you can find an elementary extension N such that N is of size kappa, right? Okay, now you can see that when we talk about the infinite models of, here you can consider this as the THM. THN is an infinite model of THMM, right? By using the theorem that we talked about earlier. Okay, now you can see that this is in theory. This is structures here. Okay, and we can talk about super large structures. And it's quite interesting that it is up to isomorphism. How many structures can we have, or do we know, like, yeah, can we get something about the structures that that is a model of our theory? Okay, and there is one extreme side of it, that is what we call the Kappa Categoricity. So we're going to consider when the structures that our theory has exactly kappa, have exactly one model of size kappa up to isomorphism. Okay, so here let kappa be a cardinal number, and let T be an L theory. We say that T is kappa categorical if for every L structures M and N, that is a model of T, if M and M has the same size, they are isomorphic, right? Or you can roughly say that it has one model of size kappa up to isomorphism. Okay, so let's look at some example. Here you can consider the empty language, right? L is equal to the empty language. And you can consider this statement. T is sigma n when n is a natural number, where sigma n is the statement that say that, okay, there exists x1 there up to xn such that xi is not equal to xj. Okay, so what does this one mean? It's mean that these structures, the universe, if you have a structure that satisfies this property, it means that the universe has at least an element, right? Because there exists x1 up to xn that are distinct, then it's say that these structures have at least an element. Okay. So what do we mean? What does this one mean? If you have a structure that satisfies this theory T, we're going to get that this M has at least an element for every n, right? So it's basically, we can say that is infinite. Okay, so M satisfy T, then M is infinite. Okay. And once we have this, so what do we have here? And if we look at the empty language, right? If you consider L isomorphisms in this language, by going back and look at the definition of L isomorphisms, you can see that L isomorphism in this case are just bijection. L isomorphism are bijection in this context. And here you can get that for any two sets, right? We can say that there are, if they have the same cardinality, then by the definition of the cardinality, you get that there is a bijection between them. So in this case, you're going to get that M is isomorphic to N. Right. So we can say that in this case, this theory that we have is Kappa categorical for every kappa, for every infinite cardinal kappa. Okay, so that's our first example. So you have an example of a theory T that is Kappa categorical for every kappa. Okay, and what else can we have? We can consider this example. Let's look at this group, this abelian group. So let's say you have an abelian group G with these identity 0 and multiplication here and plus. It's a abelian group G minus and plus. Okay. And we're gonna say that G is an abelian group G is torsion free if for every x that is in non-zero in G. If you look at n dot x, what does this one mean? It means that you look at the sum of x, nx. Right? When you look at the sum of nx, this is non-zero, right? For any n that is in that is non-zero. And we're going to say that a torsion-free abelian group is divisible if for every x in G, there exists a y in G such that n times y is equal to x for a fixed n, that is a natural number. Okay. Here we minus 0. Okay. And here we can show that this is also excluded. And here we can show that if we consider the theory of torsion-free abelian group, right, T, which consists of the axiom of abelian groups and the sentence that say that for every x, x is not equal to 0 implies that n times x is not equal to 0. For every n that is that is non-zero positive integer, and for every x, there exists a y such that n times y is equal to x when n go range over positive integer. Okay, here we can show that when we consider positive torsion-free divisible abelian groups, you can get that this is the same thing as when you consider Q vector space. Okay, so here, when you think about torsion-free divisible abelian groups, you can think about it as a torsion-free. You can consider it as a vector space over Q. Okay, why is that? The first part, right, the torsion-free part, it say that you can multiply x by n, right? And the second part, the divisible part, it's going to say that you can divide it by m for any non-zero m, right? Which means that you can consider this as n over m times x, right? So it behaves like Q vector space. And you can show that if you have an uncountable kappa, if kappa is uncountable, then you can show that every uncountable torsion-free divisible abelian groups of the same cardinality are isomorphic. So here we can show that every torsion-free, if A and B are torsion-free abelian groups, divisible abelian group, of size kappa, then you can show that A is isomorphic to B. And the idea on how you can show this is you can consider the basis, right? If you have A and B is of size kappa, and you know that it is a Q vector space, if A and B is uncountable, both uncountable, then the basis of A and B must be of the size kappa. So you can construct a one-to-one correspondence between those two bases and then construct an isomorphism from A to B. Okay, that's how we can show that these torsion-free divisible abelian groups is kappa categorical. And you can, okay, let me go a little bit quickly here. Here we have DLO infinity, which is the theory of dense linear order without endpoint. It's a dense linear order without endpoint. So what does without endpoint means? It means that for every x, there exists a y1, y2, such that y1 is less than or equal to less than x and less than y2. Okay, so here you can see that you can go infinitely large and you can go infinitely small. That's why we call this endpoint. There is no endpoint. And one of the very interesting thing, and it's a very useful technique in model theory, is what we call the back and forth construction. So let me show you the proof of this one by using picture. Proof by picture here. Here, let's say that I have a dense linear order L1 less than or equal to 1. And here I have L2 less than equal to 2. Here, okay. This proof is by Cantor. Okay, now let's see how can we prove it. Okay, the idea of this proof is if you have a two dense linear order, first thing that you can do is you can enumerate it. So here I'm gonna have A0, let's say A1, I have B0, I have B1, I have A2, I can have B2 right here, I have A3, I can have A3, B3 right here, and then B4, A4. So we enumerate the set on the left and the set on the right. And what we're going to do is we will try to construct an order preserving bijection from one side to the other side. So how can we construct that? So the idea is we're going to start by first, I'm gonna link this guy to this guy, A0 to B0. Okay, so now I have a map that I can start with. Okay, so I match one point on the left-hand side and one point on the right-hand side. Okay, so we can have a reference point on both sides. And what's next? I want to construct a bijection, right? So what should I do next? Next, in order to make sure that I use every point on the right-hand side, I already used B0. So I'm gonna look at B1. So I'm gonna look at this guy. And I'm gonna say that I'm gonna try to find a point on the left that is have the same order as B1 relative to B0. Okay, and I'm gonna pick the first guy that I found. Okay, so here A0 is already used. Nope. So next I look at A1. Okay, A1 is greater than A0, B1 is greater than B0. So I'm gonna match these two guys. Okay, now let's see what next. If I keep doing it on the right-hand side, I'm gonna run out of points. I have no way that I can guarantee that I can run out of point on the left-hand side. So what we're going to do is instead of looking from the right to left, I'm gonna look from the left to right this time. So I use A0, I use A1, I'm gonna look at A2 here. Okay, now when I look at A2, I will try to find a point on the right that is the first, that have the same standing as my A2. Okay, now let's see what should I do. And I'm gonna do it by I'm gonna pick the first guy that I find. So here we have B0 is already used, B1 is already used, B2 here. B2 here is below B0, but my A2 is above B0, so that is not good. B3 is below B1, but my A2 is above A1, so that is not good. So here we keep searching and we find B5. So we're gonna send it to here. And I'm gonna repeat this process. Next, B0 is used, B1 is used, so I go to B2. B2 gonna 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 send back to A3, something like this. And we keep repeating this process. We pick A4 gonna find some point up here, send it back here. Look at A3, A3 gonna send it to somewhere around here. Okay. Okay. And here by doing this, if you have that L1 and L2 are both countable, right? You can repeat this process like countably many times, like up to like yeah, natural number. You can get that by doing these back and forth construction. These back and forth construction, you can guarantee that every step that you do, you preserve the fact that it is an order preserving bijection, order preserving map. Here, you're trying to exhaust everything on the L2 side, so we can guarantee that this map is surjective. And you trying to exhaust everything on the L1 side, so you can guarantee that your domain is precisely L1. Okay, and what else do we have? And you know that since this structure has no endpoint, you can do these infinitely many times. And it dense as well. So if you have something in the middle, you can guarantee that you can find some point in here. Okay, so that's the idea of this construction. Okay, and we can conclude that DL or infinity is Aleph-North categorical. And one more interesting fact about this DL or infinity is for any kappa that is uncountable, you can get that DL or infinity is not kappa categorical. Okay, so that's what we have, and the idea is the easiest idea is when you have kappa is equal to the cardinality of the reals, which is 2 to the Aleph-North. Here you can consider this guy. You can have the real, right? So the reals is an example of DL or infinity, right? And you can construct another model of this by you have a real here, and you add integer, no, not integer, the rational number at the end of this guy. By doing it this way, you can see that these two are not isomorphic, because if you cut it somewhere around here, right, you should cut it somewhere around here. It will mean that on this structure, you can have that this guy only countably many objects, but this guy, it has infinitely many objects, uncountably many objects. So they cannot isomorphic. Okay. And another good things about Kappa categorical structures is it's not structure. Theory is if you have a T that is Kappa categorical for some Kappa that is larger than the language of Aleph-North, and it has no finite model, then you can show that that theory is complete. Okay. And here you can show that the LO infinity is complete because it cannot have finite model because it is dense. And it has, yep, and it has no endpoint as well. Okay, and we also know that it's a Leibniz categorical, so it is complete. Okay. And there is one more result that I would like to one application of this that I would like to show in algebraically closed field. Okay, let me go through this a little quickly. So here when we working in the language of ring, we can have an ACF, which is the theory of algebraically closed field. Okay, so what does this one say? It say that it's a field and every polynomial, right, has a root. Every polynomials of degree at least 1 has a root, right? Okay, so that's what the axiom, the theory of algebraically closed fields say. But you can see very easily that this algebraically closed field is not complete. It is not complete because it cannot say anything about the characteristic of your field. Okay, so let's consider the statement that says something about the characteristic of your field. Let's consider these for each prime p. Let chi p be the statement for every x, px is equal to 0. Okay. So it will mean that if you consider ACF with chi p, this is going to be the theory of algebraically closed field of characteristic p. Okay. And for algebraically closed field of characteristics 0, we're going to have that ACF and then not chi p for every p that is a prime. Okay. So we can have that ACFP is the theory of algebraically closed field of characteristic p. Okay. And we can show that ACFP is kappa categorical for every uncountable kappa. But to show this, we need a little bit more tools to do it. So I'm not gonna show it here. Okay, and by wash-wall test, right? We can have that ACFP is complete. So it means that is pretty nice. So here we have ACFP is complete for every prime p or p is equal to 0. Okay, now as a consequence of these 2.37, you have ACFP is complete. You can also, as a consequence of the above result, we get what we call the Lipschitz principle, which say that if you have sigma be an L-ring sentence, then the following are equivalent. The first one is if sigma is true in the complex field, then it must hold in any algebraically closed field of characteristic 0. And if it holds in algebraically closed field of characteristic 0, it must be true in some algebraically closed field of characteristic 0. These might not surprise you yet, but the next part is very interesting. Here we get that if k, if 3 holds, then you're gonna get that there are arbitrarily large prime p such that k satisfy ACF p. such that that K is an algebraically closed field of characteristic P, and K satisfies sigma. Okay. Okay, that is very interesting here. Okay, and let me sketch roughly how can we get that one. The idea is it's easier to see from 2 to 4. From 2 to 4, right? So if you have ACF 0, proof sigma. So what you can do is you can go back and look at ACF union. It's not chi p, right? Not chi p for every p that is prime. That is a prime. Now you can use completeness theorem to convert, to change from satisfiability to proof, right? So here we can get this one. Now, what can we do here? If we have that ACF P and not chi P, P is a prime proof sigma, then we're going to have we have that finitely many of sentences from here gonna prove sigma. So I can write this as ACF union not chi P1 up to not chi PK gonna prove sigma, right? So I can reduce it to these cases. So I can have that if I have ACFP union not chi P1 up to not chi PK, I can prove sigma. So what does this one mean? It's mean that ACF union not chi P1 up to not chi PK gonna satisfy sigma, which means that if I have a model of this guy, it must be a model of this guy. So if I pick a P that is larger than the maximum of these PI, I'm gonna get and I pick an algebraically closed field of characteristic P. If we have P that is larger than all the PIs, right? And I pick K be an algebraically closed field of characteristic P, then it's gonna be a model of this guy, and then it's gonna satisfy this sigma right here. Okay, so well, that is interesting here, that when you want to show that the algebraically closed, if you have an L-ring statement that is hold in algebraically closed field of characteristics 0, you can have arbitrarily large prime P and an algebraically closed field of characters P that also satisfy the same statement. Okay, and as a consequence of this, we can look at an application of this. Okay, here we can show this. Let F be a polynomial map from Cn to Cn, C to the n to C to the n. Then we can show that if F is injective, then F is surjective. Okay, how can we do that? So let me sketch the proof here. So in order to show that every polynomials, right? Every polynomials of, sorry. So here you can see that C is an algebraically closed field of characteristics 0, right? If we can show that these statements hold for, if we can translate these statements into something about in house ring sentence, that's gonna be great. So how can we do that? We're going to look at for each n and d, we're gonna let these phi and d to be a statement that say that for every polynomial map f from k to the n to k to the n of degree d, if f is injective, then f is surjective. Okay, so now you can consider this one. For every polynomials map f from k to the n to k to the n of degree d, if f is injective, then f is surjective as well. Okay, so from here you can see that the quantifier here is quantify over polynomial map, right, of degree d. But actually you can, when you think about polynomials, right? Polynomial is something that is of this form. I'm gonna write it in terms of one variable polynomial first, because that is easier to write down. So you have an minus 1, x to the n minus 1 plus blah, 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 plus a0, right? The part that determine the coefficient, the polynomial are the coefficients, right? So if you want to consider all the polynomials of degree at degree d, what you're going to do is you're going to consider all the coefficient that is possible. You need to require that the leading coefficient is non-zero, something like that. So you can convert from quantify over polynomials map into quantify over coefficients of that you need to consider here. And now if you can show that C satisfy theta in phi and d, that will for every n and d, then you're gonna get this result, right? If we have this, then done, right? So the question is, how can we get this? By using Lipschitz principle, it is enough to show that there is arbitrarily large by Lipschitz principle. It is enough to show that there are arbitrarily large algebraically closed field of characteristic P that satisfy this one. And the idea here is we're going to reduce this from, instead of consider every polynomial map in here, we're going to consider for every polynomial map f from algebraic closure of the finite field of characteristic P to n itself. So we're gonna consider this guy instead and show that if f is injective, so then f is also surjective. Okay, and how do we do that? This is also interesting. When we consider polynomial map in here, when you consider polynomial map in here, you only consider coefficients, right? So let's say you have a0 up to an, k. These are the coefficients of your f. Okay, now these coefficients are in FP ALG. The algebraic closure of FP ALG, algebraic closure of FP. But by the construction of the algebraic closure of the finite field of the characteristic P, you can get that it's equal to this guy, right? And since it is equal to this guy, you can get that there exists an n large enough such that A0 up to AK are both in FPN. So which means that you can now reduce everything from AZF map from FP, algebraic closure of FP. You can also regard this F as a map from FP to the N to the N to FP to the N to the little n here. And now you can use that the Pigeonhole Principle, because this guy is an injection map, right? You have that F is an injection map from this guy to this guy, which is a finite set, which are finite set of the same cardinality. So these map must be surjective. Okay, and then you can extend it back to this whole thing here. And you can get that this F is as a function from FP to ALG to the N, from FP ALG to the N is also surjective. Okay, so that's how we get this one. So once we have that this F is surjective, then you can get that C satisfy phi and D. And that's how we prove these Axe theorem using Lipschitz principle. You can use tools from model theory to prove some interesting result. Okay, this is something that I picked for today. And let me end here by some interesting result. So we know that when we talk about Kappa Categoricity, right? If you consider the LMT, the lengthy language, and T is the theory of infinite set, the theory of infinite set, right? Here you can see that this is Kappa categorical for every kappa, for every infinite kappa. If you consider the torsion-free abelian divisible abelian groups, this is Kappa categorical for uncountable kappa, right? And you also have DLO infinity, where DLO infinity is a Leibniz categorical, right? But not Kappa categorical for any uncountable kappa. And there is something that is very interesting. That is a result by Molle in 1965. He showed that if your language is countable and kappa is an uncountable cardinal, if T is a complete Kappa categorical theory, then you can show that for every uncountable cardinal lambda, T is also lambda categorical. Okay, so this is very interesting, and it's turned out that later Sheila's can generalize this result and show that if kappa is greater than the size of the language, so these L don't need to be countable anymore. If T is complete and kappa categorical, then for any lambda that is greater than the size of the language, you have that T is also lambda categorical. Okay, let me stop here today.
Okay, thank you, Athipat. That was a very interesting lecture. Do we have any questions for Athipat?
Sorry, can you hear me?
Yeah, go ahead.
Yes.
Okay. Firstly, I'm sorry I couldn't attend the first session. So I am briefly I briefly know the subjects and the topics, but I would like to know exactly what you covered and how I can reread that. And yeah.
Okay. I think Suyao, you have a video from last time, right?
Not yet.
I know Athipat is talking to me. What do I have? You were saying?
Do you have a record video of my previous lecture?
Yes, I do. But now this Zoom account is by Professor Koji Nakatogawa, and you see me over here. I'm not Professor Koji, but I will get it from Professor Koji Nakatogawa. The recording, and then I will try and post it on the association YouTube as soon as I can, so that everyone can have a look at the previous lectures. And also, I will try and put up all the syllabus of all these courses later. Okay, so that you can perhaps go check out the things that may be covered, and also you should be able to read it up, somewhere if you need to. And Athipat, do you think you can provide the notes?
Oh yeah, sure.
Yeah, you can send it to me, and then
I can send to you.
And I'll make it available on the website. So does that answer your question, Ali?
Yes, thank you very much. And just another question.
Yeah.
Though I didn't attend the first session, so it might be out of place a bit. I read a book a while back, Formal Languages and Their Relation to Automata, and I wanted to know how much we discussed or have discussed this topic of creating this thing and working with it, and eventually leading this into the field near about the field of computer science and stuff.
Oh, I see. You are interested in automata, right?
Yes.
Is that the question? Okay.
Yeah.
I think for that part, it's more related to the computability theory or recursion theory. You can
and also finite model theory, I think.
Right. Okay. So I'm trying to think about some books that I can recommend you, but I cannot think of it on top of my head right now.
You're recommending a book?
Yeah. Right, Jude?
Robert Soar?
Yeah, that's I think I never read that one. I will think about it. I will let you know maybe next time or something.
Okay, thanks a lot.
Okay. Any other question? Okay, if we don't have, thank you once again, Athipat, and we'll see you again in, I don't know, when is it? Let me have a look.
Next Thursday, my Thursday.
Yeah, so it could be Wednesday for people on
Right.
the Western Hemisphere.
You're
Right.
right.
Yeah. So yeah, I'll see you again next Wednesday or Thursday, depending on where you are. And yeah, just to let all of you know that I will put up the more information on the website. So please, go back to the website and check it regularly. Okay. All right, and then for the next session, there will be the second session for set theory, which is coming up in a day and an hour. Okay, so that will be on either Monday or Sunday, depending on where you are. All right, thank you, everyone. And if you have any questions, don't forget to just shoot us an email, the association email, and then I'll try to answer your questions. Okay, thank you, and see you again soon. Bye-bye.
Bye.